Hi everyone. Today's topic is we are going to determine the carrier concentration of an intrinsic semiconductor. Carrier concentration denotes concentration of charge carriers in a pure semiconductor. Intrinsic semiconductors like germanium or silicon can be taken into consideration. So here the symbol used for carrier concentration of an intrinsic semiconductor is Ni. The formula which we are going to use is based on law of mass action. Ni square is equal to Ne into Nh, where Ne denotes the number of electrons in the conduction band of the intrinsic semiconductor per unit volume. Similarly, Nh denotes number of holes in the valence band of the intrinsic semiconductor per unit volume. This product of Ne and Nh expressions and then taking the square root of this product will give the intrinsic carrier concentration final expression. Now the two diagrams have been taken here, the energy band diagram. Here Vb denotes valence band and Cb denotes the conduction band. Eg is the forbidden energy gap and Ec is the lowest energy level of the conduction band and Ev is the highest energy level of the valence band. The first diagram shows at T is equal to 0 Kelvin the intrinsic behavior of the semiconductor, and at T greater than 0 Kelvin, at T Kelvin, when the temperature of the semiconductor is kept at T Kelvin, here the movement of the electrons from the valence band to the conduction band is considered, and here at T is equal to 0 Kelvin the empty conduction band. There will not be any free electrons or conduction electrons available. Now we are going for the explanation for carrier concentration of an intrinsic semiconductor. It can be defined as the number of charge carriers, electrons and holes, electrons in the conduction band, holes in the valence band per unit volume. The number of charge carriers per unit volume of the intrinsic semiconductor. Now, the general formula for Ni is Ne into Nh, as we said earlier, the whole power half. So our work is we need to find the number of electrons in the conduction band of an intrinsic semiconductor and the number of holes in the valence band of the intrinsic semiconductor. In the diagram, Ef denotes Fermi energy level. Fermi energy level. Now in the second diagram, which shows when the intrinsic semiconductor is kept at T Kelvin, the limits of the valence band is minus infinity to Ev and the limits of the conduction band is Ec to infinity. From Fermi distribution function, the probability of electron occupying a particular energy level can be determined using f of E, that is Fermi distribution function expression. And for holes, 1 minus f of E should be used. These are the prerequisites. So to find intrinsic carrier concentration, we need to determine number of electrons in the conduction band of the intrinsic semiconductor per unit volume, and we have to determine the expression for number of holes per unit volume of the intrinsic semiconductor in the valence band. Then Fermi distribution function of electrons occupancy is f of E and holes is 1 minus f of E. So now when the temperature is increased above 0 Kelvin, the electrons in the conduction band will be moving to the electrons in the valence band moving to the conduction band. So the second diagram shows, let us assume there are 10 electrons moving from the valence band to the conduction band, and here there are holes created in this valence band. We are going to find how many number of electrons are present in the conduction band. Here how many number of holes are present in the valence band. So now the general formula to determine number of electrons in the conduction band of the intrinsic semiconductor is Ne is equal to integral. In the conduction band, the limit is, where is the limit here? Look at the diagram. We are going to see only the conduction band, that is this particular part should be taken into consideration. Therefore, we are going to consider limit is EC to infinity in the conduction band. The energy levels in the conduction band is the lowest energy level EC and the highest energy level is considered as infinity. And the general formula is the density of states as in the metal and the probability function to know how the electrons have been distributed among various energy levels in the intrinsic semiconductor. So Z of E dE, it is about the density of states and it is about the probability function. We are going to substitute the expression for density of states. So integration EC to infinity Z of E dE is pi by 2 8 me by h square the whole power 3 by 2 e power half dE. This is density of states. And f of E is 1 divided by 1 plus e power e minus ef by kBt. Here me denotes the effective mass of the electron. Usually in metals, m will be used. M denotes the mass of the electron. Usually m0 will be considered, that is 9.1 into 10 power minus 31 kg will be considered. Here in semiconductors, the band theory is used for the semiconductivity phenomenon. Therefore, the mass here will be replaced by the effective mass of the electron and the effective mass of the hole, because the charge carriers are assumed to be moving in the periodic potential. So they are accelerated. The mass will not be constant, just like as m0 or m in the metals. There will be change in mass of the charge carriers, which will be considered in semiconductors as me and mh, the effective mass of the charge carriers respectively. So coming back to this, Ne is equal to integral EC to infinity. The density of states expression is taken and the Fermi distribution function for finding out the electron occupancy is written here. Now we are going to find how many number of electrons are present per unit volume of the intrinsic semiconductor. Here pi by 2, 8 meh square, all these are constants. So these can be taken out of the integration sign. Pi by 2, 8 me by h square, the whole power 3 by 2, ec to infinity. E should be replaced by, here in the metals E is used, whereas here look at the diagram. For simplicity we have taken only 10 electrons are occupying the conduction band. So let this be the energy level considered. So the range of electrons occupying the energy levels are from E to EC. EC is the lowest energy level and E is the, up to this the electrons are filled at this particular temperature, T greater than 0 Kelvin. So the electron occupancy is considered from E to EC. Therefore, the difference between the energy level in between these two, the electrons are occupying in the conduction band, E minus EC. So it is just like, for example, if E is equal to 2 electron volt and E is equal to 2.1 electron volt and EC is equal to 2 electron volt, E minus EC is 2.1 minus 2, that is 0.1 electron volt. Based on how much amount of thermal energy is consumed by these electrons, they are occupying the energy levels. So this 0.1 electron volt is, for simplicity we are considering. Therefore, E here should be replaced by E in metals for density of states expression. Here in the case of semiconductors, E should be replaced by this range, E minus EC, which is equal to some amount of energy. Just like here I have considered it as 0.1 electron volt, it should be generalized form considered as x kBt. That is because of the energy consumed by it based on how much amount of temperature or thermal energy is given. So kBt, there may be 0.1, 0.2. It depends on how much energy, thermal energy is consumed by it. So generally E minus EC is taken as x kBt. So here E should be replaced by, here E should be replaced by E minus EC. So this is for metals, the density of states. It is rewritten for semiconductors in the case of electrons in the conduction band of the intrinsic semiconductor. So E is replaced by E minus EC power half. Now 1 by 1 plus E power E minus EF by kBt. To explain about this, look at E minus EF here. That is E minus EF is considered as, I am taking a different color. So here E is here, EF is here. E minus EF is the positive value, because E is at the higher energy level when compared with the EF, which is in the middle of the forbidden energy gap. Therefore, in this Fermi distribution function, 1 divided by 1 plus E power E minus EF by kBt. T is that particular temperature where we are going to derive this expression. E minus EF is positive. Therefore, E power E minus EF by kBt is very much greater than 1. So here this 1 can be neglected. Therefore, I am writing this equation as 1 divided by E power E minus EF by kBt, neglecting 1, since exponential of E minus EF by kBt value is very much greater than 1. This is T is greater than 0 Kelvin, and then E minus EF will be of positive value also. Because of this we are neglecting 1. I am rewriting the above equation as Ne is equal to pi by 2 8 me by h square, the whole power 3 by 2, Now integral EC to infinity E minus EC power half, and then writing this as, I have dE also here, I am writing this dE here. So dE, while I am taking this to the numerator, EF becomes positive and E becomes negative. Therefore, E power EF minus E by kBt. So this is the required equation, the basic equation to determine the number of electrons in the conduction band of an intrinsic semiconductor. Now, all these energy levels E, EC, EF and the difference in energy, everything is inside the intrinsic semiconductor. So the usual unknown parameter should be taken into consideration for this. We told that E minus EC is equal to x kBt. E minus EC is equal to x kBt as a generalized form. So here I am going to consider E minus EC is equal to x kBt. Some amount of energy will be there. Based on the difference between E and EC, the value of x will be changing. That is, there will be change in temperature, then surely there will be change in the electron occupancy in the conduction band. Based on the difference of E minus EC, the value of x will be changing. Therefore, we are going to find E minus EC as x kBt. Now we are going to find E is equal to what? E is equal to, I am taking this towards the other side. Therefore, EC plus x kBt. Then I am going to differentiate the above equation with respect to x. Therefore, dE by dx, or I can take this dx on the other side also. X becomes 1 and then dx into kBt. Now substituting E minus EC as x kBt and then E as EC plus x kBt and dE as dx kBt in this above equation, I will get pi by 2 8 me by h square the whole power 3 by 2 integral. Now I am not going to write the limits here. I am going to replace all the energy values in terms of the usual unknown value called x. E minus EC is replaced by x kBt power half. So instead of E minus EC by EC power half, I am replacing it with x kBt. Then E power EF minus E divided by kBt. Here I have EC plus x kBt as E. Therefore, EF minus, here it is energy with a negative sign. So I need to substitute a negative sign for both EC and x kBt. So x kBt by kBt. And then dE is replaced by dx kBt. So dx kBt. Now consolidating the above equation. Before that, let me explain about the limits change also, because all the energy notations have been replaced by x. Here can you see this? E minus EC is replaced by x kBt, and then E is equal to EC plus x kBt, dE is equal to dx kBt. So now the limit will also be changing from the limits of E to limits of x. So limit change. For limits changing, for energy levels, the lower limit is EC in the conduction band, and the upper limit is infinity in the conduction band. Now this limit has to be changed for x. Look at the formula here. E minus EC is equated with x kBT. The difference in energy in the conduction band is equal to x kBT. Now, when E is in the position of, now from the diagram I am going to explain, the lower limit is EC. When E is in the position of, in the diagram you can see that E is here. When E is in the position of EC, then what is x kBT? Look at this. When E is in the position of EC, then there won't be any difference at all. Or mathematically we can also consider, when E is in the position of EC, then EC minus EC is 0. Therefore, x becomes 0 here. Therefore, when E is in the position of EC, x becomes 0. So, the lower limit for x is 0, whereas previously the lower limit for E is EC. Now, applying the upper limit infinity in this equation. Previously, E is in the position of EC. Now, if E is in the position of infinity, look at this, infinity is the highest energy level here. If E is in the position of infinity, then fully it will be filled. Therefore, still it becomes infinity because EC is the lower energy level. Therefore, going to the change in the limit, it also becomes infinity. Therefore, we are going to change the limit from E limits to x limits. So, EC is replaced by 0 and then infinity is infinity here also. Now, comparing the formula or consolidating the equation, pi by 2. This equation has been consolidated. Pi by 2, 8 me by h square the whole power 3 by 2 integral 0 to infinity. Here look at this equation. Here we have x power half, kBt power half. Here I have kBt power 1. So I will be writing x power half kBt power 3 by 2 because 1 here, half here. I'll get 1 plus half in the powers, therefore kBt with the power 3 by 2. And then I'm writing this exponential value as e power ef minus ec by kBt and then e power minus x kBt by kBt. So I'm rewriting this equation as just like e power m minus n by 2 as e power m by 2 into e power minus n by 2. So I'm writing this as e power ef minus ec by kBt and then e power minus x kBt by kBt. So I'm going to write this as e power ef minus ec by kBt into e power minus x kBt by kBt. So here I have dx. So I'm writing the dx here also. Now this kBt power 3 by 2 is taken towards 8 me by h square. So consolidating pi by 2 8 me kBt by h square the whole power 3 by 2. Also x values should be within the integral sign and the other than x values just like ef minus ec by kBt can be taken out of the integration. Ef minus ec by kBt. then integral 0 to infinity. This x power half can be written as root x. Then here kbt get cancelled off. We get e power minus x dx. Here the value of integral 0 to infinity root x e power minus x dx is considered as or taken as the value pi power half by 2 or root pi by 2. Root pi by 2. Therefore, substituting the integral values in the above equation, we get NA is equal to pi by 2 8 ME KBT by H square the whole power 3 by 2 e power EF minus EC by KBT, and then instead of this we are going to write pi power half by 2. So this pi power 1 and pi power half is taken as pi power 3 by 2 and 2, here we have a 2, 4, then 8 ME KBT by H square the whole power 3 by 2 e power EF minus EC by KBT. Now this pi power 3 by 2 is also taken inside this bracket. So I'll get 1 by 4 8 pi ME KBT by H square the whole power 3 by 2 e power EF minus EC by KBT. The usual formula to express the above equation, number of electrons in the conduction band of intrinsic semiconductor is 2 into 2 pi ME KBT by H square the whole power 3 by 2 e power EF minus EC by KBT. So this is the general expression. How we got this, in the sense it can be explained by, we have 8 here, 8 power 3 by 2. So here I am going to write it as 8 power 3 by 2. It is a note. I am writing this 8 as 4 into 2 power 3 by 2 and then 4 power 3 by 2 into 2 power 3 by 2. This 2 power 3 by 2 is taken here, and then this 4 power 3 by 2 is 2 square power 3 by 2. So 2 get cancelled off. 2 cube is equal to 8. So instead of this 8 power 3 by 2, I am going to substitute 2 and then 2 inside this 3 by 2 bracket, and then here 8 outside the bracket. So this 4 and 8 get cancelled off. We get this 2 here. In this way we got the final equation for number of electrons in the conduction band of intrinsic semiconductor per unit volume. So here we started with the general expression for finding number of electrons in the conduction band of an intrinsic semiconductor per unit volume, integral z of E dE f of E. This is density of states equation and the Fermi distribution function for electrons, because we are going to find electrons in the conduction band of the intrinsic semiconductor. The general formula for density of states is pi by 2 8m by h square the whole power 3 by 2 e power half dE. Here two corrections we have made based on semiconductivity phenomenon. M is replaced by Me, and then e power half is replaced by e minus ec power half. And then this Fermi distribution function, this 1 can be neglected because the exponential value is very much greater than 1. Then substituting E minus EC is equal to x kBT and then rearranging E is equal to EC plus X kBT. Differentiating E with respect to X, we get dE is equal to dx kBT. Then substituting all these values in the above equation, changing the limits, that is for E the limit is EC to infinity. When it becomes X, it is 0 to infinity. So substituting this and rearranging, consolidating, simplifying, we arrived up to this equation, and the integral value can be replaced by root pi by 2 or pi power half by 2, and then consolidating, we arrived up to number of electrons in the conduction band is equal to 2 into 2 pi me kBT by h square the whole power 3 by 2 e power ef minus ec by kBT. So this is the equation 1, which is used to determine number of electrons in the conduction band of the intrinsic semiconductor per unit volume. Let this be part 1.